Alright, in this video, we study a special class of differential equations that are called separable differential equations. A separable differential equation has the following form: y prime minus f of x times g of y is equal to 0. Here, this function f of x is just a function of x alone, and this g of y is a function of y alone. This is called separable because we can separate them. So let's write y prime as y dy dx. Yeah, and move this to the right hand side. And we have this. Then let's divide both sides by g of y. Then we have 1 over gy here. And so formally, let's multiply both sides by dx. And we have dy here. And on the right hand side, we have f of x and dx. So in this way, we can separate y and x to different sides. Then we integrate both sides. So we just integrate the left-hand side with respect to y. So we get some function of y. And if we integrate the right-hand side with respect to x, then we have some function of x. In this way, we can at least implicitly solve the differential equation for y. And this procedure is called separation of variables. All right, let's see an example. Suppose we have this differential equation. Y prime is equal to x times y. And case 1, if y is equal to 0, this is a constant function, then this is a solution of this equation, right? Because y is 0, so the right-hand side is always 0, and y prime is also 0, so the left-hand side is always 0. So this is a solution. Now, another case. Suppose y is not a constant function equal to 0. Then we can divide both sides by y. So y prime divided by y and x. And we can integrate both sides. So dy over y and x dx. So the left-hand side becomes log of y, and the right-hand side becomes 1 over 2x squared plus constant. Of course, the constant may appear on the left-hand side too, but we can just put constant term all on the right-hand side. Now, by the way, this log is, of course, natural logarithm, and by taking the exponential function of both sides, we have y equal to exponential of 1 over 2x squared plus c, but this plus c can be just replaced with another constant, so 1 over 2x squared. So this c prime here is exponential of c is c prime. Okay, so this is just a constant, and this is just a constant, so we can just represent all constants like this. So this is the solution. So y, if not equal to 0 constantly, then it should be this function. However, this general solution actually includes the first case, this one. If this c prime is equal to 0, then this is just a constant function equal to 0. So therefore, we can just conclude that y is equal to some constant, possibly 0, times exponential of 1 over 2x squared. Here, the solution like this one, including this undetermined constant, is called a general solution. On the other hand, y equal to, for example, just exponential of 1 over 2x squared. So this is, of course, a special case of the general solution where this constant happens to be equal to 1. So this is called a special solution. Next, let's consider a physics problem where a body of mass m falls in the air pulled by the gravity of Earth. So the gravity of Earth will be, the force will be m times g. G is the constant. That's the gravity of Earth. And since it's falling in the air, it feels air resistance that is proportional to the velocity v of the body. So here, the equation of motion is given by m times acceleration is dv dt. So t is time, right? And we take the coordinate system in this direction. So the force is mg in the positive direction. And the air resistance is negative kv, where v is the velocity here. So this is an differential equation of separable form. So let's try to solve it. Okay, so let's separate them, and from here we get dv over mg minus kv equals to dt over m. So let's integrate both sides, and for the left hand side we have log absolute value mg minus kv, and let's see, negative 1 over k, and here tm plus constant. Let's move this negative k to the right hand side. So log mg kv equal to negative kt over m. Let's redefine this constant by multiplying the negative cases. Constant is still a constant by multiplied by a constant. So okay, so this is it, and this constant c can be determined from the initial condition. Let's say initial condition is, so the velocity at time 0 is 0, so it was just sitting still before it falls. So this is called initial condition. So if we put t equal to 0, then this is 0, and at that point velocity is 0, so this is 0. So that means log mg is equal to the constant c. Okay, so the constant c is this, and let's take the exponential function of both sides, and kv, that's exponential of negative kt over m. And since c is log mg, so that is times mg. And let's solve this for v. So that will be, first move this to here and move this to here. Let's see, kv is equal to, let's see, mg. So we have mg here, so let's factorize them. That's 1 minus exponential of kt over m, and divide both sides by k. We have v over k here. So this is the solution. By the way, v is a function of time, right? So this is the final solution we have got given the initial condition here. So let's plot this graph. Plot the graph of this function. Let's see. So time t is here, and velocity. So this is exponential function. K is positive, m is positive. So this exponent here is negative because t is positive. So t increases from 0 to infinity. And so this exponential function converges to 0 here. And when t is equal to 0, then this is equal to 1. So 1 minus 1 is 0. So at this point, it's 0. So this is consistent with the initial condition. So we actually specified the initial condition so that the velocity is 0 at time t equal to 0. So it's 0. But as time goes by, this exponential function term converges to 0, so it will approach this constant. So that will be, so this will be mg over k. So it will look like this. Okay, so when t goes to infinity, well, of course, but before t hits infinity, the falling body will hit the ground, so it will stop sometime. But unless that happens, the velocity increases, but gradually converges to this value. So at this point, the gravity, the force of gravity and the force of air resistance, they balance each other. Next, consider a differential equation of this form. dy dx is equal to f of y over x. So this is a function of one variable, but the variable appears only in this form, y over x. In this case, we say such a differential equation is homogeneous. Okay, and this has a nice property. And if we change a variable u equal to y of x, then we have y is equal to ux. And if we differentiate y with respect to x, y prime is equal to u plus u prime x. So u is a function of x, of course. So if we replace this y over x with u and y prime by this one, u plus u prime plus x, then what we have is here. So we have, let's see, so this one, the left hand side will be u plus u prime x, and the right hand side is f of u. So we have u prime x, f of u minus u, and let's divide. So this is actually the separable form, separable differential equation. So we have du over this one, f of u minus u is equal to dx over x. So this can be solved by the separation of variables. So let's see an example. Consider this differential equation. Y prime is equal to xy over x squared plus y squared. At first sight, this doesn't look like it's a separable differential equation, but if we divide both numerator and denominator by x squared, we have y over x and 1 plus y over x squared. So if we replace y over x by u, then we have u plus 1 plus u squared here. So it's a separable, it's a homogeneous differential equation. Therefore, it is actually a separable differential equation. So as we explained before, let's put u equal to y over x. Then we have y equal to ux, and y prime is equal to u plus u prime x. So just use this, replace this y prime here, and we have u plus u prime x. equal to u over 1 plus u squared, and u prime x is equal to u this minus u, and let's simplify a bit. That's what is it, u minus u cubed 1 plus u squared. Okay, so let's divide both sides by this, and by this we have u du u plus u squared over, this will cancel, u cubed negative here, and dx over x. So let's see. Okay, so let's integrate both sides. Okay, the left hand side, let's see, we have 1 over u cubed plus 1 over u du. So that is 1 over u squared and negative 1 over 2, and plus that's log of u, and the right hand side is just log of x. Let's put constant here. So after all, we have, let's see, let's put this minus sign inside, and 1 over 2u squared minus log u is equal to log of x plus constant. So let's put u equal to y over x back. So here we have 1 over 2, so it's x over y squared, and log of y over x, and log of x plus c. And let's see, so we can expand this log y over x as log of y minus log of x, but with this negative sign we have this, so we have log x both sides and they can be cancelled. So after all, we have 1 over 2x over y squared minus log y equals to some constant. I think this is as far as we can get. We cannot simplify this anymore. Okay, so that's it. So we are done. This is the solution, I mean implicit solution of the differential equation given by this. As you can see, not all differential equation can be solved explicitly, so sometimes we must be satisfied with this kind of implicit solution. Implicit means it cannot be expressed as y equal to some function of x alone. Here, x and y are mixed, so it's implicit. Okay, that's all for this video. See you later.